So in the last video, we were in the middle of problem number 3. I had just entered the data and graphed it. And I was talking about what we think it looks like. In this case, I think that I do think it does look a little concave up. I think there is some concavity there. So my guess is it's not linear, but it's not extremely exaggeratedly concave. So if you wanted to check linear, that's fine. But if you're in a hurry, I think you would be safe in saying that this is either going to be exponential or logarithmic. So let's go ahead and take a look at the Let's go ahead and take a look at the exponential regression. I don't know what I'm doing now. Stat calc xbreg. So there's my exponential regression. Let's go ahead and calculate the SSE. Now that is a very small SSE right there, 0.00003. So really, I think that we would be safe in assuming that we do have an exponentially distributed data. Now, if you were not sure and if you had plenty of time to check, you could go ahead and check linear and logarithmic and check their SSEs. But I'm pretty confident that, let's look at the graph. You would be hard-pressed to get a better fit than that, I think. So I'm going to go ahead and assume that this is exponential. And now I'm going to answer question B, which says solve the equation g of x equals 10. That's actually a calc intersect question. So I need to let y2 be 10. And let's go to the table and see how long it takes to get to 10. I was already kind of high up there because of my previous work. So actually I'm too far. So this happens around 6 or 7. So if we go from 0 to 10, that'll be plenty. And then we'll do zoom fit. There's our intersection. And it looks to happen at 6.12. All right. Number 4. The population P of a bacteria colony is modeled by P of T equals 300 times 1.2104 to the T, with time measured in hours after 9 a.m. on February 11th, 2018. What was the population of the colony at 9 p.m. on this same day? So 9 p.m., that's 12 hours after 9 a.m. So we'll first need to, actually let's do this. Let's turn our stat plot off and clear everything. And clear your functions. And now enter your function. Okay. And now evaluate the function at 12. And there is our population at 9 p.m. Question 2. How long did it take for the colony to grow from the initial population to 1 million? So we actually have to put in the full 1 million value here because our unit is ones. So this is a calc intersect question. So 1 0 0 0 0 0 0. I think that's a million. And we'd better go to the table to see how long it's going to take to get to this. Notice 1e to the 6, that's scientific notation. So how long is it going to take? We might even should go in jumps of 5. Although look here, we're already going in. You know what? I am gonna increase my jump, my increment. Well, that didn't take long. There we go. So 47. We're already at 2 million. So let's go to the window and let's go to 40. And do, actually let's go to 45 just in case, and we'll do zoom fit. And hopefully we'll see our intersection. I think we're going to get it. There it is. And so our intersection is 42.481. That's 42.48 hours. What is the colony's hourly growth rate? Okay, so the hourly growth rate, here's the hourly factor. So the hourly growth rate is just this number minus 1 times 100, so that's going to be 21.04%. Because we were already in hours. Our model is already in hours. So what about the continuous hourly growth rate? All right, so there we actually have to do something. So if we want RC, if you forgot what the formula is, let's go back to our formula list. RC is ln of the growth factor right here. So all we need to do is take ln. I don't know. It doesn't want me to do that. Okay. All right, ln of 1.2104, and then I'll need to multiply that by 100. So 19.10. So we're moving along now to number 5. Solve the linear system 8x equals 1.65 plus 3y and 9.24 plus 2x equals 4y. So this will be a 2 by 2 linear system because we have two variables, but the first thing we need to do is arrange it. So it needs to look like this. Now I'm putting the x first. It doesn't really matter. I could have put the y first. 2x minus 4y equals negative 9.24. So make sure you understand why all these are positive or negative and how I move things around here. And then we'll go to our calculator. Actually, let me go to the whiteboard so that I can kind of write what my matrices are. So my matrices are going to be 8 minus 3 2 minus 4 inverse times 1.65 over negative 9.24. This is my matrix of constants. This is my matrix of coefficients. So this is A inverse times B. And from here we go to the calculator. Matrix A is going to be a 2 by 2. And there is that. And matrix B is going to be a 2 by 1. And now we'll call up the matrices. Don't forget to invert A. And there you go, there's your solution. X is 1.32 and Y is 2.97. Number 6. So here's one of our nice mixture problems of juices. Suppose that large quantities of two juices are available. Juice number 1 is 100% apple juice, juice number 2 is 66% apple juice, and 34% cranberry juice. How many gallons of each of these two juices must be mixed in order to obtain 200 gallons of a juice that is 82% apple juice and 18% cranberry? So with any word problem, your first task is to identify the question and the variables. So how many gallons of each of these two juices? That's the question. And the two juices are, this one and this one. So I'm going to go to the whiteboard and write down my variables. I'm going to let X be gallons of apple juice. That's juice 1. And I'm going to let Y be gallons of, that's J1. This is J1 for juice 1. And this second one is gallons of the cran apple juice, which is juice 2. And it's important that you identify your variables very clearly here. Okay, so let me move this around a bit so you can see what I want you to see. So the first equation that I would write is just a simple total amount equation. If I add these gallons to these gallons, then I get 200, because that's what I want to make, is 200 gallons of a third juice. And from there, I'm going to write what I like to think of, in this case anyway, is a pure cranberry equation. I could also write a pure apple equation. I don't know, it doesn't really matter. We actually have 3 equations we could write, but we only need 2 of them. So any of the 2 will work. So I'm just going to do cranberry. And so I want to think about cranberry contributed by J1 plus cran from J2, and that needs to equal the total final cran. Okay, so what are all those things? So the cranberry contributed by juice 1. Juice 1 is all apple juice. So, and by the way, the amount of juice 1 is X. So the total amount of juice 1 is X. But how much of that, what percentage of that X is cranberry? 0. So that's 0x. And then from juice 2, which the total amount is Y, and the portion that's cranberry is 34%, so that's 0.34 of the total Y. And what does that equal? My total amount is 18% of 200, so that's 0.18 of 200. And we will have to finish this problem in the next video. Okay.